Hello everybody, and welcome to our video reviewing exponential and logarithmic functions. So most of this video is going to be a review, but we will tie a few things. We'll look at the graphs of these functions, exponential and logarithms, and you'll notice some things related to limits that are going to come up in more detail later. But mostly we just want to make sure we've got a fresh review on the topic so that when we get to dealing with the limits of these things, they make a bit more sense. So first of all, let's recall the definition of an exponential function. A function f of the form f of x equals a to the x, where a is greater than 0 and not equal to 1, is called an exponential function with base a and exponent x. So a couple quick things. These restrictions are really important because we won't be describing the type of function we want to describe if we don't include these restrictions. For example, if a was equal to 1, we would have 1 to the x, which would just be equal to 1. So that wouldn't be a very interesting function at all. And if a was 0, we'd have 0 to the x, which is 0 everywhere except for when x is 0. 0 to the 0 is undefined. And if a was negative, we would get some bizarre problems because then we could have something like a is negative 1, and x could be 1/2, which is the square root. And then we'd have the square root of negative 1, which is imaginary, right? You can't take the square root of a negative number, at least not in the real number system. So we put these restrictions on a to make this function behave nicely. Otherwise, we get a lot of discontinuities for negative values, and for 0 and 1, we get functions that are just constant values, so they're not particularly interesting. But assuming that a is a positive number, other than 1, then the domain of this exponential function will be negative infinity to infinity because it will be defined for any exponent you can plug in. And the output, as we'll see, will be between 0 and infinity. So strictly positive outputs for this basic exponential function. So to re-summarize this stuff, exponential functions are defined for all real numbers, x. The graph of an exponential function is a continuous unbroken curve, and the rules of exponents apply for all real numbered exponents and positive bases. Now, this is sort of the rough definition of the exponential function. I'm not going to go crazy into depth on the tricky details, but recall that if we have a fraction, so if I have a to the 1/3, for example, that really means the cubed root of a, and we're going to talk about that more in depth. So that means immediately that we can deal with fractions as exponents. And if we have something that isn't a fraction, if we have irrational numbers, then we could look at the behavior of the exponent value with fractions that approach that thing. So like, for example, pi, 3.14, blah, 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 blah. I could look at fractions that are approaching that number, like 3 1/10 or 3 14 100ths, so forth and so on. And I would be able to look at the limiting behavior as that thing approached pi. So we can deal with all sorts of numbers with the exponential function, but we won't go into the intricacies too much with that. Okay, so let's go ahead and take a glance at these rules of exponents. So again, this is just a refresher. Sometimes I find that students when they're trying to remember their rules of exponents, they're not really thinking about what the rules mean, and so they'll make silly mistakes on them. So I want to illustrate what these rules mean explicitly, mostly with some examples and some with some real proofs to show why that rule is true, just to make it a little bit more clear so you don't mix up your rules, hopefully. So a to the x times a to the y equals a to the x plus y. So what does that mean? Well, remember, an exponent means repeated multiplication. So if I have a squared times a cubed, that really means a times a multiplied by a times a times a. And really altogether, I'm multiplying a by itself 5 times here, right? So I'm adding 2 plus 3 is 5. So in other words, the exponent counts the total number of repeated multiples of something. So I add up each of those numbers to get my total number. Now, if I have an exponential raised to another exponent, that's like repeating that exponent. So if I have a squared cubed, that's a times a cubed, which is a times a multiplied by itself 3 times. So altogether, I have 6 products of a, or 3 groups of 2, right? That's 3 groups of 2, and 3 times 2 is 6. So that's why if we have an exponent to an exponent, we actually just can multiply those exponents together for our final expression. Okay, if we have a times b to the x equals a times a to the x times b to the x, okay, why is that the same thing? Well, if, for example, I have a times b, we'll do a simple one, cubed, that's a times b, a times b, a times b. And of course, I can multiply in any order, so I can put all of my a's, I can multiply first, and then all of my b's, and that's a cubed times b cubed. So this rule is just another way of saying I can multiply in any order. That's all we're doing here. But remember, this exponent has to be the same, otherwise we can't pair each a and b up together. So the statement wouldn't make sense if the exponents weren't identical there. Okay, so now let's look at a to the x divided by a to the y. That's equal to a to the x minus y. And so this is pretty straightforward. If I look at a cubed divided by a squared, that's a times a times a divided by a times a. And for each factor of a on the top, I can cancel a factor on the bottom. So I just get left with 1 factor of a. So in other words, 3, I remove 1 for each one I have in the denominator. 3 minus 2 is 1. All right, so a to the x over a to the y is a to the x minus y. Okay, a to the 0 equals 1. This is one that students often find a little odd, but actually it makes perfect sense if you think, hey, all of these rules are built on a really basic fundamental understanding of what the exponent means, repeated multiplication. So all of these rules need to be self-consistent. So if I take a to the x divided by a to the x, well, any number divided by itself should be 1. But my quotient rule here tells me that this should be a to the x minus x, which is a to the 0. So a to the 0 has to be the same thing as 1. Now here we've got another rule, that a to the negative x power is equal to 1 over a to the x. And again, that's a pretty straightforward one, but we'll do it in the opposite direction. 1 over a to the x. Well, 1 we just saw was the same thing as a to the 0. And then if I use my quotient rule, this gives me a to the 0 minus x, but that's the same thing as a to the negative x. So in other words, 1 over a to the x equals a to the negative x. Okay, so just a couple more here. This first one, we mentioned this in passing before. A to a fraction is to the fraction 1 over q is the qth root of a. So we have to think about this one a little bit different. So for example, if I write the third root of x, really the definition of that is the number which when multiplied by itself 3 times gives me what's inside x. So if I look at x to the 1/3 power, and I multiply x to the 1/3 3 times, what do I get? I get x to the first power. 1/3 plus 1/3 plus 1/3 is 1. So these two things are the same thing, right? So they are effectively saying the same statement. What number multiplied by itself 3 times is x? But we can generalize that to qth times. What number multiplied by itself q times is a? So these two notations are exactly the same thing. All right, and a to the p over q. So here, if I have a to the p, and I take the qth power, that's just a to the p to the 1 over q power, and we know that we can multiply powers. So p times 1 over q is just p over q. That's a to the p over q. Same thing. Okay, so hopefully that was a little refresher on those rules, and if maybe one or two of those was not sticking with you super closely. Hopefully that'll help. Okay, so now let's take a look at the graphs of the basic exponential functions. So these are exponential functions without any shifting. So we're just looking at what's the behavior of this a to the x thing. Well, if a is a number bigger than 1, then when we graph this, when I plug in x equals 1, I get a. When I plug in x equals 0, I get 1. And when I plug in x equals -1, I get 1 over a. And we'll talk more about this later, but we see that, hey, if I raise x to a higher power, I should say, and a is bigger than 1, when I multiply by a again each time, I get a bigger result, so this thing keeps growing. And if I have a negative power, I'm getting 1 over a to that power, and so I'm dividing by something bigger, so the fraction actually gets smaller. Now, on the other hand, if a is less than 1, this thing flips around, and we can see that where if I plug in 1 here, I get a, but a is smaller than 1, right? So maybe 1 should be on my graph here. So that's maybe not even the best spot for it. Or actually, 1 should be there. My bad. That's where 1 should be. So where was I? When I plug in 1, I get a. When I plug in 0, I get 1. When I plug in -1, I get 1 over a. So we see that this behavior really just flips. So now when I have bigger powers, since a is less than 1, this thing gets smaller and smaller. All right, so one of the reasons that we care a lot about exponential functions is compound interest. Right, so any banking institution is giving you loans or is paying you for putting money in a savings account. They're going to use some type of compound interest. Now, typically, when you take out or when you put money in a bank, like a savings account or a bond or something like that, you get compound interest. And so what happens is they take your amount of money, that's your principal, P, and they're going to add a certain amount of interest each period that they pay out. So how many times interest is compounded. So let's say that, let's say n here, we're going to do like a little example. N is the number of times compounded per year. Let's say n equals 12. So that means you're compounding every month. And for ease of use, and you would rarely get this kind of interest rate on a private account like a savings account, but let's say your interest rate was 5%. That makes things easier. So R, 5%, but we need to deal with this in decimal form, 0.05. And then the number of years, T, is, how many times, how many years you charge, you collect interest on it. So number of years. But here's the key thing. N times T is the total number of times interest is collected. Right? If I collected n times per year and I multiply that by t, right, that's going to be the total number of times I've collected interest. So just as an example, so I'll use nt as this column here. So if I collect interest 0 times, that means I've just put my money in the bank. If I collect interest once, that means I've got my principal and I've also added 5% on top of that. So I'm multiplying the principal by 0.05 and adding it to p. And if I factor that p out, I get p times 1.0.05. Hold on, that's not quite right. Let me rephrase that. So this is the annual interest, 0.05, but I only take 1/12 of that per month, right? That's what the n is for. So each month I take 1/12 of my annual interest rate, then I factor my p out, and then I get this. Okay, so what happens next? Now the second month goes by, and so I take my original principal, or I take the amount I had before, I should say, and I add another 5% on top of that. So, so I want to make sure I factor this out carefully. Factor out the p, factor out this expression. I get p times 1 plus 0.05 over 12 times. Oh, and again, I forgot to divide by my 12 there. 1 plus 0.05 over 12. So again, p times this plus p times this times my interest for the next month. I get this, but this factor happens twice, so I get p times 1 plus 0.05 over 12 squared. All right, so that should make sense. What is this squared? This is nt. This is exactly what we've got in the formula here. All right, so I've just gone through this example to illustrate what's happening with this formula and why this is our general formula for compound interest. It does exactly what we expect it to do. All right, it just takes that principal, multiplies it by 1 plus our yearly rate divided by the number of times per year, all raised to the power of how many times we've compounded that interest. Okay, so with that out of the way, let's go ahead and move forward to a key fact here. So one of the exponential bases we use really commonly is base e. And so we're going to talk about why base e is so important in so many applications. But the first application, we'll deal with that a lot more in other sections and other problems. But the first application I want to talk about is just this plain old interest formula. So it's very difficult to prove this with the tools we have now. Once we get some tools from Calculus 2, we really can prove this with those tools. It's still a tough problem, but we'll at least cite this fact that the expression when h goes to infinity, 1 plus 1 over h to the h power, approaches a fixed number. Now, that fixed number, there should be a bunch of dots there, it goes on forever, right? It's a transcendental number, but it is finite, right? And because it has an infinite decimal representation, we gave it a special name called e. So we can show that this value does converge to something, and we can use approximation techniques to find any number of decimals we want to approximate the value for e. But the question is, why do we care about the limit of this particular form? All right, so, well, let's just real quick, we'll restate this, and then we'll look at why we care about that. So the definition of e is the number that is the result of the limit as h goes to infinity of 1 plus 1 over h to the h power, which we can rewrite in the equivalent form e equals the limit as x goes to 0 of 1 plus x to the 1 over x power. Now, that might seem a little bit weird, but all we're doing here is letting x equal 1 over h. And so then if h is going to infinity, then x is going to 0. All right, so all I'm doing is a little substitution. If h goes to infinity, x goes to 0, so I rewrite the limit in terms of x. I replace 1 over h with x, and similarly, h gets replaced with 1 over x. So they're the same limit, just written in a different form. Okay, so why do we care so much about the result of this limit? And one of the main reasons that we care so much about this result is continuous compounding interest. So quite often, when you are being charged interest, banks will compute their interest based on continuous compounding interest. And the idea of continuous compounding interest is, what happens if we take our previous formula, a equals p times 1 plus r over n to the n times t, and we let n approach infinity. So I think what should be kind of obvious is that the more often you collect interest, the faster your principal or your total amount grows. So, of course, if a bank is giving you a loan, they want their interest that they earn to grow as quickly as possible. So they might ask, well, what happens if we just let the number of times we collect interest get bigger and bigger and bigger and approach infinity? So what we're going to do is just examine the result of that limit as n goes to infinity of p times 1 plus r over n to the n times t. And how are we going to do this examination? Well, we're going to let x be equal to r divided by n. And we're going to do a little substitution on this limit. So if n goes to infinity, this fraction, r is a fixed number. It's your interest rate. It's not going to change, or it shouldn't. It's a fixed interest rate. So if n goes to infinity, then that implies x is going to approach 0 here. So what do we get? Well, we get the limit as x goes to 0 of p times 1 plus x to the, and now we've got n times t. So let's try to substitute n, since we don't want to limit as n goes to infinity anymore. We see that if we multiply n across, we get n equals r divided by x. So this is r divided by x times t. And now I'm just going to use some basic limit laws, or not limit laws, I mean basic exponential laws, to rewrite this slightly. So this I'm going to write as 1 over x times rt. And we know from our exponent laws that we can write that as, instead of the product of the numbers in the exponent, I can rewrite this as 1 plus x to the 1 over x all to the rt power. And one more little step here. The continuity and convergence theorem says we can move our limit inside of a continuous function. And so we move that limit inside this expression. And this is the thing that we defined as e. So that's why we actually define e the way it is. Because e is the number that results from taking this limit, and since it has an infinite decimal point expansion, we just gave it a nice name and said, let's call this e. It's roughly 2.71-ish, right? So that's what e is. E is just the result of this limit that comes up in the continuously compounding interest formula. Now this type of limit also comes up in certain population growth behaviors, but we're not going to talk about that right now, but it does come up in a whole lot of applications. Okay, so now that we're done with continuous compounding interest, let's go ahead and move on to something else. So we're going to talk about logarithms, but in order to understand what a logarithm is, we have to recall what an inverse is. So just as a quick aside here, one moment here. So little aside. So y equals f of x. So if y equals f of x, f and hold on, let me. All right, if y equals f of x is a one-to-one function, meaning each output only has one corresponding input, there's two equivalent definitions. The first one is that f inverse is the function such that f inverse of f of x equals x, and f of f inverse of x equals x, or the equivalent definition that y equals f of x if and only if x equals f inverse of y. Now we deal with inverse functions a lot in calculus, so these definitions are very, very important. What they basically say is, if you plug an inverse of a function inside the input of that function, you get the inner input back. And it doesn't matter which order you do that in. Or equivalently, inverse functions say you switch inputs and outputs. Both of these statements are completely equivalent, and which version of this definition for inverses you're going to use is just dependent on which one's more convenient for the application. Okay, so since exponential functions are one-to-one, they have inverses, and logarithms are just the notations for those inverses. We didn't have a basic algebraic expression already that we could use to notate them, so we create the notation of logarithms just to describe or notate the inverses of exponentials. So if f of x equals a to the x power, its inverse is written log base a of x. That's it. So with these definitions of inverses in general, we see that y equals log base a of x if and only if x equals a to the y. We switch the inputs and the outputs of our functions. That's what logarithms are. They're inverses. And likewise, if I plug the inverse into the other function, I get back x. So a to the power of log base a of x is just x. And log base a of a to the power of x is just x. We're plugging one function into its inverse. Okay, so with that said, we're going to go ahead and tackle some examples of using logarithms. And what you'll notice is that in just pretty much all of these problems, we're just going to be using one of these two definitions of inverses to solve them. So let's tackle this first one. Write 144 to the 1/2 power equals 12 in logarithmic form. So there's a number of ways we could do that. We could think of this as switching inputs and outputs, but I actually prefer to go, hey, this is an exponent with base 144. So I'm going to take log base 144 of both sides. And log base a of a to the x is x. X in this case is 1/2. So this implies that 1/2 equals log base 144 of 12. And now it's in log form. There's no exponents, there are only logarithmic expressions. Okay, so a couple quick notation notes. If we don't write a base explicitly, we mean base 10. That's called the common logarithm. And if we write ln of x, that's just a shorthand for log base e of x. We're going to use the base e a lot. And so this just makes it easier for people to type up. You put ln of x, and that means log base e of x. And then you don't have to worry about trying to type subscripts every time you type out natural log. All right, so write 1 plus log of 10,000 equals 5 in exponential form. So the first thing I'll do is move the 1 across. I get log of 10,000 equals 4. Keep in mind, this is implicitly base 10 here. And I'm just going to raise each side of this equation to base 10 of the exponent, or in the exponent of base 10. So a to the log base a, because remember, implicitly, there's a little base 10 there. A to the log base a of x is x. Done. That's exponential form. Okay, so let's evaluate some of these things. Evaluate log base 3 of 27. Well, again, there's a number of ways I could tackle this, but I recognize that 27 is just 3 cubed. So this is log base a of a to the x, which is x. And for b, now this one's a little more involved. Log base 3 of log base 2 of log base 5, and I recognize that 25 is 5 squared. log base a of a to the x is x. So this innermost logarithm is going to just become 2. But of course, 2 is the same thing as 2 to the first power, and log base 2 of 2 to the x is x. So this is log base 3 of 1. Okay, well, how do I deal with that one? Well, there's 2 ways. I could think of 1 is 3 to the 0, or I could remember that 3 to the 0 is 1, which implies that log base 3 of 1 is 0, because we're switching inputs and outputs. 0 is my input, 1 is my output. If I switch to the inverse function, 1 is the input, 0 is the output. Either way is fine, but log base 3 of 1 is 0. Solve log base 6 of x is 2. I want to get rid of this logarithm. How do I do that? Well, I'll just take 6 and raise both sides to the exponent position. Six to the log base 6 of x, a to the log base a of x is x. So this is x equals 6 squared, which is the same thing as saying x equals 36. Solve log base 3 of 1 over 81 equals x. Well, first I'll rewrite 1 over 81 as 1 over 3 to the 4th. And I can rewrite 3 to the 4th, 1 over 3 to the 4th as 3 to the negative 4th. And log base a of a to the x is x. Again, it's just the same thing over and over. All these problems have a different flavor. They look a little bit different, but they're the same question. It's just applying these definitions repeatedly. So let's go ahead and summarize some properties of exponential and logarithmic functions. So all of these, I've just written the equivalent properties next to each other. So let's just take a look at them. A to the 0 is 1. Log base a of 1 is 0. Switch your inputs and outputs. A to the first power equals a. Input is 1, output is a. Log base a of a equals 1. Switch your inputs and outputs. What is domain and range? Domain is the set of inputs. Range is the set of outputs. Switch your inputs and outputs means switch your domain and range. The y-intercept is y equals 0, but we are switching x and y values for exponential functions. So that means that the logarithmic function has an x-intercept at x equals 0. The exponential function has no x-intercept, so the logarithmic function has no y-intercept. Switch your x and y values. The x-axis is a horizontal asymptote for the exponential function. That's y equals 0. So the y-axis, which is x equals 0, is the vertical asymptote for the logarithmic function. Switch your x and y values. Same thing. The exponential function is 1-to-1. The logarithmic function is also a 1-to-1 function. And both of these functions are increasing if a is bigger than 1, and both of these functions are decreasing if a is between 0 and 1. And we'll see that part a little more clearly in these graphs. So let's take a look at the graphs for log base a of x. So here in red, I have the exponential function plotted, and you're switching your x and y values. That's the key thing here. So notice, if this is 1a for the exponential function, then the point down here on the logarithmic function is a1. And likewise, if this is a point BC, you switch the point value to CB. And what happens is that you get a mirror image over y equals x, right? If I look at the point 0, 1, the log function has the point 1, 0 included. If I look at negative 1, 1 over a, the log function has 1 over a, negative 1. So again, every point on the logarithmic function is a mirror image over the y equals x line. That's what inverse functions do in general. So here, when we look at a between 0 and 1, so remember our exponential graph looked a little different for that one. It was flipped around. But the same logic applies. which is that if I'm looking at the logarithmic function, I just switch all my x and y points. So from 1 over a becomes a, and 1a becomes a1, and so forth and so on. So again, we still get a mirror image over y equals x. It just looks a little different here. All right. So here, this is just the exponential functions moved out, so we can just look at the clean graph of the logarithmic function. So what do we see? We see, if we look at the 3 key points, plotting 1 over a, 1, and a for our x values, we get -1, 0, and 1 respectively. And we get the same values. When we plug in a, we get 1. When we plug in 1, we get 0. When we plug in 1 over a, we get -1. The only difference is a bigger than 1 or between 0 and 1? That's what changes the shape of this graph. In both cases, we still have a vertical asymptote here. That doesn't change. Okay, so the last main topic we're going to touch on in this review video is logarithmic rules, or rules of logarithms, in particular the product, quotient, and power rules. So a lot of times people, I think, make these overly complicated, but if you understand the exponential functions, the truth is that you understand the logarithmic function rules, because they're really just the same rules. Remember, inverse functions switch inputs and outputs, and just like inverse functions switch inputs and outputs, their rules switch inputs and outputs too. So here, notice that this product is outside of the functions a to the x and a to the y, with a sum inside of the function a to the x plus y. So what happens with the logarithmic rule? Instead of the product being outside the function, the product is inside and the sum is outside. And for the quotient rule, your quotient is outside the functions with subtraction inside the exponent. For the logarithm, the quotient is inside the logarithm with subtraction outside. For the power rule, the exponent has an exponential outside of the function, becomes multiplication inside. The logarithmic function has an exponent inside of the logarithm with multiplication outside. So again, if you know these exponential rules, all you got to do is flip them around, and that's your logarithmic rules. Now, of course, what I just said was not a rigorous justification for these rules, so we're going to just look at the proof for one of these rules, and you can basically adjust this proof slightly and tweak it to get the proofs for the other logarithmic rules. But we'll run through that real quick. So let log base a of x equal u, and log base a of y equals v. So we're just naming these two log values as u and v. But remember, we can switch inputs and outputs to switch to an exponential form. So if I switch inputs and outputs, I get x equals a to the u and y equals a to the v. So that means the product x times y is equal to a to the u times a to the v. And my exponent rule gives me that x times y then is equal to a to the u plus v. Now if I take log base a of both sides of the equation, I get log base a of x times y equals log base a of a to the u plus v. But log base a of a to a power is that power. So log base a of xy equals u plus v, but again, u plus v is just this. So log base a of xy equals log base a of x plus log base a of y. So you can prove these rules. It's just clever manipulation algebraically using the definition of these inverse functions. Okay, so let's go ahead and tackle an example. Given that log base 10, or log of x equals 3 and log of y equals 4, evaluate log of x squared times y cubed inside the logarithm. Well, I have to somehow figure out how to rewrite this to where I have expressions that are just log of x and log of y. But I have this product inside, so if I use the product rule, what do I get? I get log of x squared plus log of y cubed. And now I have an exponent inside each of these logarithms. So if I use my exponent rule for logarithms, that tells me I could just move the exponent in front of the logarithm, This is 2 times 3 plus 3 times 4. All I've done at this stage is just plugged in the number for each one. 2 times 3 is 6, 3 times 4 is 12, 6 plus 12 is 18. Okay, that's it for that one. Right, log of the square root of x cubed plus 1 over x squared plus 4 in expanded form. Okay, so I just want to illustrate what that means real quick. Expanding means taking expressions that look like this left side and turning them into expressions on the right side. And condensing, which we sometimes do as well, means taking expressions that look like the right-hand side and moving to the left. So a question I often get is, when do I stop expanding, or when do I stop condensing? You stop when you no longer have expressions that are on the one side. So if I'm expanding, as soon as I don't have anything that looks like this left side, I stop. If I'm condensing, as soon as I don't have anything that looks like the right side, I stop. All right, so back to the problem. I've got a quotient here, so using my quotient rule, this is log of the square root, but I'm going to write that as x cubed plus 1 to the 1/2 power, instead of writing the square root, minus log of x squared plus 4. And now I see I have an exponent inside this logarithm. So now I'm going to use my exponent rule. And I get 1/2 log of x cubed plus 1 minus log of x squared plus 4. And notice I don't have any products. I don't have any quotients in here. And although I do have powers, those powers are not to the entire input. They are only to a single expression. So I can't apply the power rule here because the power rule requires that that power apply to everything inside. So no power rule here. So we're done. Okay, now write 3 ln of x minus 1/3 ln of x squared plus 7 in condensed form. So first I'll use my power rule or my exponent rule. You can call it either, same thing. So this is ln of x cubed minus ln of x squared plus 7 to the 1/3 power. But remember, 1/3 power is the same thing as the cubed root. So I'm just going to write it like that. And then I can use my quotient rule and write this as ln of x cubed over the cubed root of x squared plus 7. Okay, so here's one more big topic, the change of base formula. So all the change of base formula says is that for any logarithm, as long as a and b are not equal to 1, which should be kind of obvious because we don't define logarithms with bases equal to 1, then log base b of x can be converted to another base as follows. Log base b of x equals log base a of x divided by log base a of b. And the key here that trips people up a lot is that a can be anything you want. Except it has to be positive and not equal to 1, of course. Our usual restrictions on bases applies. So you can pick a to be whatever you want. Now most calculators, and you should discover why this is the case in Calc 2, but most calculators can only deal with natural logs and log base 10, unless you're dealing with a much more advanced calculator that usually is just doing the conversions on the fly for you. But generally they only deal with natural logs or base 10 because they have to use approximation techniques and they can't store infinitely many versions of logarithms. So typically when dealing with a calculator, we will choose base e, the natural log, or we will choose base 10. So usually we will write log of x over log of b, or ln of x over ln of b, usually. but there's no requirement that we use those specific bases. Okay, so let's just look at the proof. This proof's just a clever trick. It's actually very simple, but it's so simple that it seems bizarre that it works. So y equals log base b of x, switch my inputs and outputs, gives me b to the y equals x. If I take log base a of both sides, I get log base a of b to the y equals log base a of x, and my exponent rule lets me pop that y out in front. So y times log base a of b equals log base a of x. Divide the log base a of b across, and y equals log base a of x divided by log base a of b. But remember, y was log base b of x. So we can pick whatever power we want, right? Whatever base we want, a. It will always work. As long as it's positive and not equal to 1, I should say. Okay, so let's go ahead and use this to solve a problem. We're not going to use a calculator on this one, but we are going to use change of base. And what I realize is that 4 and 8 are both powers of 2. So I choose base 2. And I rewrite this as log base 2 of 8 divided by log base 2 of 4. And then I can rewrite each of those further. 8 is 2 cubed. And 4 is 2 squared. And log base a of a to the x is x. So up top we get 3, and in the bottom we get 2. And so the answer is 3/2. And I believe that's it. All right, that's it for this one. Thank you for watching.